In this video tutorial, I want to discuss with you how we can compare two samples with a two-tailed two-sample independent t-test. So for this example, we are looking at a particular biomarker in patients, and we assume the biomarker might have a concentration. We measure everything as milligram per cubic decimeter, so that is the concentration of the biomarker. And we have a sample of patients who suffer from a particular disease, and we also have measurements from healthy volunteers, and we want to figure out whether the biomarker is potentially a good indicator for the presence of the disease. So our question would be, do patients from this disease have a different concentration of the biomarker than, for example, healthy volunteers? So what we can do, of course, is we can calculate the mean and the confidence interval for this biomarker concentration in patients and healthy volunteers. So we can do these calculations, and if you are interested in how we do these calculations, I will leave the link to a video in the description here. So we find that for the patient biomarker concentration, it is 13.9 plus minus 5.3 milligram per decimeter cubed. So this is this and this value here. And for the healthy volunteers, we have 19.6 plus minus 3.9 milligram per decimeter cubed. Okay, so the question now is, are these two means different from each other? And of course we would say, yes, of course they are different from each other. But are they really different? Are they enough different from each other so that we can say, yes, they are different? So let me explain the conundrum that we have. We have two samples here. So one is these are the healthy people and these are the disease people. And we look at them and say, is this difference between the healthy and the people with the disease, is it actually statistically significant? Now, we cannot really compare samples with each other. And that is because of the problem with sampling error. So we have one sample here of the healthy and one of the disease people. But if we took another sample with also 4 volunteers from the healthy group, this healthy sample might be slightly different. Why? Because we choose different volunteers. We choose a slightly different method. So the samples will be different, and they differ from each other in the sampling error. Sampling error. That's the difference between these two samples. But is the sampling error smaller or larger than the difference between the healthy and the diseased people? And that is actually what a t-test does. So in a t-test, what we do is we take our samples, healthy and diseased, and instead of directly comparing them with each other, we look at the underlying populations. So this is the population, and this is the population for the diseased. And we ask, instead of comparing the samples, we compare the populations from which these samples have been drawn. And we ask the question, are these populations different from each other? Can we distinguish these different populations? Or does it look like something like that? are the populations indistinguishable from each other. And that is basically what a two-tailed independent two-sample t-test does. So what we are going to do is a two-sample, because we've got two samples here, two-sample independent, the samples are not dependent on each other, independent two-tailed t-test. That is what we are going to do, and in this test we are comparing the population that we can estimate from the samples. So what we do first is, as per usual, we always formulate our null hypothesis. So in this case we say, for our null hypothesis, we say the population mean of the sample 1 is the same as the population mean of sample 2. Or we can write this mathematically as sample mean 1 minus sample mean 2 equals population mean 1 minus population mean 2 equals 0. So here that would be this case here, where we have no difference between the populations. And in words we can say something like, there is no difference between the population mean 1 and population mean 2, and any observed difference that we see between the two different samples can be totally explained just simply by sampling error. The alternative hypothesis, H1, would be the population mean 1 is not the same as the population mean 2, so population mean 1 minus population mean 2 is not equal to 0. And we can say there is a difference between the population mean 1 and population mean 2. And the observed differences that we see in the samples can only be explained by the sampling error and an additional effect, namely that they come from different populations. In the next step, we calculate a significance level, or we set a significance level alpha, that's our type 1 error, and very often we will set that to 5% or equals 0.05, and that then helps us to make a decision, and we can set up some decision rules. So we can say if the p-value that we are going to calculate in a minute is smaller than this significance level, we reject the null hypothesis. We say it's very unlikely that we get this result if the two populations are the same, and we accept the alternative hypothesis. On the other hand, if the p-value is larger than this significance level alpha, we fail to reject the null hypothesis. So we say, well, these two populations are so close to each other we can't distinguish them. Now in Excel, luckily there is quite a nice way of calculating that. So in Excel we can calculate the p-value, and we do that with the Excel function equals t.test, and it comes up with the suggestion. It takes 4 values. So the first one is our array of sample 1. So I highlight the cells here, drag it down with the mouse. That's our array 1, comma, we do array 2. That's this one here, comma. We want a two-tailed test. We only say they are, the alternative hypothesis only says they are different from each other. We don't specify whether one is bigger or the other, so that's why it's a two-tailed test. And we assume that both samples have a different variance, a different standard deviation, and we know that they are different because we can calculate the standard deviations here and here. So therefore we pick 3 as the option here for this particular test. Close the brackets, and we get a p-value of 0.045. So 0.045, that's our p-value. Here again is the equation that we can use. And now what does that mean? We are going back to our decision rules and we say, right, the p-value is smaller than our alpha, so 0.045 is smaller than 0.05, and therefore we would reject the null hypothesis and we would accept the the alternative hypothesis. So this means we have sampling error and an additional factor, so therefore it indicates that there is a significant difference between the concentration, between the mean of the concentrations, mean of biomarker concentrations, between patient and healthy people. And healthy volunteers. So actually there is this difference, and we observe this difference, and there's very clear indication that there is a difference based on our sample. So I hope this makes sense, and thank you very much for watching.